You know, in cosmology, you've got your deep puzzles. And then you have problems that are so stubborn, so persistent, they start to challenge the very foundation of how we see the universe. The Hubble tension, it's one of those problems.
And for years, the whole thing has boiled down to this one kind of maddening question. When we look at the universe close to home, it seems to be expanding at one speed. But when we look way out at the ancient, distant universe, it seems to be expanding at another. So on one hand, you've got data from the cosmic microwave background, the afterglow of the Big Bang, which points to an expansion rate, the Hubble constant, of about 68. But then you have measurements from nearby supernovae that give us a value closer to 74. And let me be clear, this is not a small disagreement. Now, for a long time, cosmologists have been sort of watching this problem from a safe distance, like watching a storm roll in. But a recent paper suggests a whole new approach. Think of it like this. It's the difference between just watching lightning flash and being Ben Franklin, actually flying a kite into the storm to interact with it. This paper isn't claiming to have the final answer, not at all, but it's offering a new way to really engage with the problem itself. And that brings us to the crucial question we're going to dig into. What new capability does this new model actually give scientists? And maybe just as important, where do its limits lie?
All right, so here's our roadmap. First, we'll get a better handle on this cosmic measuring problem. Second, we'll look at the big core assumption this new model decides to change. Third, we'll see how it actually tries to recreate the disagreement we see in the data. And finally, we'll put up some guardrails and talk about what this model can and cannot do.
Okay, let's dive into the problem itself. This stubborn gap in what is otherwise our incredibly successful standard model of the universe. So, that standard framework, it's called the lambda CDM model, or just lambda CDM. Now, for what we're talking about today, its most important feature is this fixed, unchanging value called the cosmological constant. That's the lambda. This constant is supposed to explain why the universe's expansion is accelerating. It's really a cornerstone of modern cosmology. But here's the kicker. This nearly 10% difference between the two Hubble measurements, it's just way too big to be a simple mistake. I mean, our measurement precision has gotten down to about 1%, so this isn't just some noise in the data. It is a genuine tension, and it suggests our standard model might be missing something. And this is where the new paper comes in. It proposes a different model. They call it the thermal vacuum model, or TVM, and it does it by changing one of the most fundamental assumptions of lambda CDM. Let's just walk through what the researchers actually did. It starts with a pretty simple but really profound shift. First up, they take that fixed, unchanging cosmological constant, and they just remove it from the standard equations. Then they substitute it with something new, a dynamic thermal vacuum energy. And the crucial part is that this energy changes over time as the universe expands and cools. And this is kind of the magic trick of the whole paper. The authors come up with a new formula for cosmic expansion based on this dynamic energy. But they don't just stop there. They do something fascinating. They run a simulation. They ask, what would happen if you lived in our TVM universe, but you analyzed it using the tools and assumptions of the old lambda CDM model? From that, they calculate what they call a running Hubble constant. Now, it's really important to get this straight. This paper doesn't involve any new telescopes or new observations. This is all theoretical work. It's testing a new explanation by seeing if it can make sense of the conflicting data we already have. So, what happens when they run this simulation? What does the model actually predict? Well, it tries to recreate the very disagreement that it was designed to explain. And the core finding is pretty wild. The model predicts that if you look at the nearby universe, where the light hasn't been stretched out much, what we call low redshift, the old LCDM formulas would spit out a Hubble constant of about 74. But if you use those exact same formulas to analyze the distant, high redshift universe, you'd get a value of about 68. So let's just break that down, because this is the crucial takeaway. The model doesn't make the tension disappear. Nope, it predicts it. It suggests the disagreement isn't a mistake in our measurements, but an artifact of our tools, an expected result if we live in a TVM universe, but we're looking at it through a lambda CDM lens. Okay, that's a really compelling result, right? But, and this is a big but, to really understand this, it is absolutely essential that we're clear about the boundaries, about what this paper is and is not claiming. Let's be very clear. This paper does not prove the thermal vacuum model is correct. All it does is establish it as a viable candidate that could explain this one specific problem. It's not some grand theory that solves everything else in cosmology. And most importantly, it's a theoretical model. It now has to be tested rigorously against other observations and other data sets.
So let's circle all the way back to our original guiding question. Based strictly on what the authors have shown us here, what can we say now that we couldn't say before? Here's the precise breakdown. First, a new kind of interaction is now possible. Scientists can take data, old and new, and test it against this alternative framework. Second, the nature of our uncertainty has changed a bit. The possibility that the tension is an artifact of our model, not our data, just got stronger. But here's what hasn't changed at all. The fundamental question of which model, LCDM or TVM, is actually the right one. That is still completely up in the air. And that leaves us with one final and kind of provocative thought. This paper took a constant and made it dynamic to explain one puzzle. So it really forces us to ask, what else about our understanding of the universe might change if our most fundamental idea about the energy of empty space turns out to be incomplete?